Hello, boys and girls. Mr. Jim Meany. Wanted to come to you with a little bit of review, I think today and tomorrow, maybe even Wednesday, about some things you're going to see on your post test on Thursday and Friday. So let's take a look at a couple of examples here. So first one here says multiply 3 and 85 hundredths times 10 to the fifth. Now, many of us probably going to get our calculators out and put this in, but I look at this exponent and it's a positive 5. So that means this number is going to get larger. Now remember, we're doing powers of 10, the base of 10 there. So I just think I'm going to move the decimal point, whatever this exponent says, that many places to the right if it's positive, or that many places to the left if it's negative. Well, in this case, the exponent is positive. So I'm going to move this decimal point to the right, and I'm going to move it right 5 spaces. So if I think about it, it's right here. Now I'm going to move it over 5 places. 1, 2, have to move over 3 more places. 1, or 3, 4, and 5. So I'll just fill in these humps here with zeros. So the decimal actually moves. It doesn't stay here. It has traveled all the way to the end. So my new number would really look like this. It would be 385,000. That is 3 and 85 hundredths times 10 to the fifth power. So I've taken scientific notation and transferred it or converted it into standard notation. Let's look at another scientific notation. And I know it's scientific notation because the first number is greater than or equal to 1, but less than 10. So this says 8 and 304, what is that? Thousandths times 10 to the sixth power. The exponent's positive, so that means the decimal is going to move to the right. So if I put my decimal point right there, and I want to move it to the right 6 spaces, well, let's move over 1, 2, and 3, and I will move it over 3 more. 1, 2, and 3. So that's a total of 6. I'll put 0 there to hold that place value. And now that would really look like, remember, the decimal has moved all the way to the end of that 0. So I come put my comments here. So that really converts to, I've converted 8 and 304 thousandths times 10 to the 6 into standard notation to 8,304,000. Now I need to write these in scientific notation. So now I need to take the decimal. Now remember, there's no decimal here, but really, when I don't see it, it's all the way at the far right of the number. And I need to move it in between two numbers where the number is going to be greater than or equal to 1, but less than 10. Well, the only place I can move it is between this 4 and 3. So it's going to be 4 and 375 thousandths. Now, because of scientific notation, it's times 10. Now let's think about it. I one from here to here. How many places did I move over? 1, 2, 3, 4, 5, and 6. So this is standard notation into scientific. I know it's a positive exponent because from going to about $4.37 to $4 million, I have gotten larger. I've become larger, so that's why it's positive. If I look here, same thing. I want to convert this to scientific notation. Where can I put the decimal point at so that it's greater than or equal to 1, but less than 10? Remember, the decimal point's all the way here to the far right. I'm going to put it between the 1 and the 2. So this becomes 1 and 24 hundredths. Now, times, because we're doing scientific notation, we have a base of 10. Now, how many places did I move over from here to here? Let's see. 1, 2, 3, 4, 5, 6, and 7. So it's 10 to the 7th power. And finally, find the product of 2 and 3/10 times 10 to the 3rd. So again, this is scientific notation. I want to convert it to standard. This positive exponent tells me to move the decimal point 3 places to the right. This number's going to get larger. So it will look like this. I'll move over 3 places, so that's 1, 2, and 3. So add 2 zeros there. So that gives me 2,300. Okay? That helps you with little scientific notation and standard notation. Let's look at some more examples here. I'm not going to do all these. Let's go down to this one here. The GCF, the greatest common factor of 27, 48, and 60. Well, let's look. 27, 48, and 60. Well, we got to break these into prime numbers. So let's make our factor trees. 27 is 3 times 9. Well, 3 is prime. Perfect. 9 is 3 times 3. So my prime factorization of 27 is 3 times 3 times 3. Let's go to 48. Let's make our factor tree. What times what is 48? Let's try 8 times 6. Okay, neither of those are prime, so now we say 6 is 2 times 3. So we have 2 and 3 are both prime. Let's find the prime numbers of 8, or let's try to break it into prime numbers. So we know we have 4 and 2. Well, 2 is prime, so now let's break up 4. 2 times 2. 1, 2, 3, and 4, so that's 2, or that's 4 2s. 2 times 2 times 2 times 2, and let's go times 3. So there's the prime factorization of 48. Now I can always check this and say, hey, 3 times 3 is 9, times 3 is 27. Okay, good. 48 is 2 times 2 times 2, which is 8. 2 times 2 times 2, which is 8. 2 times 3, which is 6. 6 times 8 is 48. Now let's try 60. I know 60 is 6 times 10, but neither of those numbers are prime. They don't have only two factors, one itself. So let's break up 10 into 2 times 5. That is prime. They're both prime. And then 6 would be 2 times 3. Those are both prime. So I go 2 times 2 times 3 times 5. Now with greatest common factor, I have to find the one or two numbers that they all have in common. Well, let's take a look. I don't go horizontally, I must go vertically. Well, they don't all have 2, so I can eliminate that. I don't have to worry about looking at the 2's. They don't all have 5, so I can eliminate that. Now they all have a 3, but the most 3's that they all have in common is 1. So the greatest common factor of 27, 48, and 60 is 3. I don't worry about the scraps with greatest common factor. Now if I do least common multiple, there's why I pull in the scraps. And let's take a look at an example real quick. Get rid of these, and let's do number 18. So we have 6, 8, and 12. Well, the prime factorization of 6, what times what equals 6 is 2 times 3. Those are both prime. Prime factorization of 8 is 2 times 2, which is 4, times 2, which is 12. And then the prime factorization of, is 8, sorry. 2 times 2 is 4, times 2 is 8. Now the prime factorization of 12 is 2 times 2, which is 4, times 3. Now with greatest or least common multiple, we look at what they can chunk together, or what some of them have in common, or what all of them have in common. Well, they all have a 2 in common, so I'm going to chunk all those 2's together. So that's 1, 2 times. They both have, two of them have a 3 in common, so there's my other 3. They have a 3 in common, times. These both have 2's, so that could be chunked. Here's my scrap. I'll just throw that at the end. 2 times 3 is 6. 2 times 2 is 4. 6 times 4 is 24. So the greatest common factor of 6, 8, and 12 is 24. If you want, try these at home. This should give you an answer of 21. This should give you an answer of 72 if you want to figure it out. And if I remember correctly, this gives you an answer of 16. And this gives me an answer of 12 if you want to try to figure those out on your own. All right, let's take a look at another problem here. Evaluate each algebraic expression for the given variables, or given variable value, sorry. So this says 7 times n, 7 times something, minus 34 plus n. Now we have to substitute n in. We're going to substitute 9 in for n. So now this becomes no longer 7 times n, but 7 times 9 minus 34 plus 9. Now let's do order of operations. We have multiplication, subtraction, addition. Well, first I'm going to multiply. 7 times 9 is 63. 63 minus 34 plus 9. Okay, now I have subtraction and addition. Now I know in PEMDAS, the A comes before the S, but remember, we do addition and subtraction. Whatever comes first from left to right. Well, going from left to right, we have subtraction first. So let's go 63 minus 34. That's a 13. Okay, so that gives me of what? 13 minus 4 is 9, I believe. 5 minus 3 is 2. So now I have 29 plus 9. 29 plus 9 gives me 38. Try to solve this one at home. This one should give you an answer of 48. Be careful with this because you're going to put 2 times 3 to the third power. So cube the 3 first and then minus 3 squared. Do this first and then times it by 2. But this should give you an answer of 48, and we just did this one was 38. All right, last examples here. Translating word phrases into algebraic expressions. So we have a number. I don't know what it is, so I'll call it n. I'm going to multiply n times the sum. Sum means to add something, and I have to add 12 plus 32. Here's the trick. I have to multiply n times the sum, so I got to find the sum first. So what I would do with this is I want to show that I want to find the sum first. So what can I use to put around numbers to show, hey, do this first? That's right, parentheses, and then I will times that by n. Next one, 12 less than. Well, 12 less than means I need to take 12 away from something. It means to take it away from something. Whenever I take it away from something, it must come second. Now, quotient means to divide. I need to divide a number, which I don't know what it is, and 20. So I could do, hey, n divided by 20 minus 12. So we know that this number is 12 less than it divided by 20. Last one, the sum. Sum tells me to add. Sum tells me to add. It tells me to add 59 times the number. So I got to take 59 times means to multiply. Multiply it by some number. I don't know what it is, so I'll call it n. And then fancy word for add. And then add 3 because we got sum here. Sum tells me to add. Hope this helps you out. Take care. Bye.